So the last thing we discussed was the calculation of the minimum frame length for the case of CSMA CD. And we said that the minimum frame length is based on the fact that when the transmitter sends at time t1, the frame transmission should last for 2 propagation times to go all the way to the end of the cable and come back. So before the signal goes all the way to the end of the cable and come back, if the sender finishes the transmission, then even if there is any collision, it won't feel it. And because it finished the transmission of the frame, it will flag this frame as successfully sent, which in that case is wrong. So to avoid that situation, the frame transmission has to be long enough for the signal to go all the way and come back. And we said that the condition for this is simply, the rule is simply that the T transmission equals double the propagation time. Okay? So from that, we can get the frame length equals 2 propagation time times the data rate, the maximum data rate, or the bandwidth. So because the transmission time is actually the frame length divided by the bandwidth, right? Divided by the channel data rate, channel maximum data rate, which means that the frame length is double the propagation time times the bandwidth. So this is of course the minimum. So this example illustrates this notion. So if I have a network of CSMA CD with a bandwidth of, or a maximum data rate of 10 megabits per second, if the maximum propagation time is 26 microseconds, what is the minimum size of the frame? So we know that the minimum size of the frame is 2 times the propagation time times the bandwidth. So the transmission time is double the propagation time, which is in that case 51.2 microseconds. So this means that in worst case, a station needs to transmit for a period of 51.2 microseconds, which is double the propagation time. So the transmission itself has to be at least this or more. If the station waits, or if the station spends 50 microseconds, then there is a possibility that a collision might happen down within the cable, and the station that is trying to send will not feel it. Okay, because it finishes transmission in less than this propagation time, or double the propagation time. So this means that the minimum size for the frame length is simply 10 megabits per second, which is the channel bandwidth, times double the propagation time, which in that case is 512 bits. So the minimum size of any frame in that network should be at least 512 bits. Okay? Divided by 8, that makes it 64 bytes. It turns out that this is actually the same calculation for the standard Ethernet, the 10 base T Ethernet. The minimum size of the frame is in fact 512 bits. I'm not sure if you have studied that in 455, but we explained that in 455, that the minimum frame length is actually 64 bytes. Okay, so that's coming from the fact that the propagation delay for a cable of length, what is the maximum length for Ethernet cable? 100 meters. 100 meters. So in that case, the propagation delay is around that number, and because of that, the minimum frame length is about 512 bits. Okay, so that's the flow chart for the CSMA CD. Okay, as we can see, there are some similarities compared to pure Aloha and slotted Aloha. So in that case, there are three major differences. If we need to distinguish this flow chart from the pure Aloha or the slotted Aloha, we need to keep in mind three major differences. The first one is that for Aloha, you don't have to do any persistent strategy. If you want to send, just send. However, in CSMA CD, we need to do carrier sensing, and we need to do some kind of strategy for whether if the channel is idle, we send right away, or we have to sense every duration of time, or what happens if we find the channel idle, then we don't send right away, we have to flip a coin with a specific probability, and things like that. So this procedure is what we call persistent strategy. We didn't have to do that in pure Aloha. If we want to send, just send, right? So that's one major difference, which is illustrated in that block, that we need to apply one of the persistent strategy, whether it's one persistent, non-persistent, or p-persistent. So that's one. So this flow chart is this block is actually reflected by one of the three flow charts that we have studied for the persistent strategies. Okay, so that's replaced in that block here. If I get out of that block, that means that I'm eligible to send. Okay, which means that I perform the carrier sensing. It seems that the channel is idle. I flip a coin, the probability says that I need to send. Okay, so I can just send. The second major difference, so that's the first one in that block. The second major difference is the fact that when you send, there is a collision detection. Okay, again, that's one major difference that did not exist in pure Aloha or slotted Aloha. In slotted Aloha, I didn't have to do any collision detection. Okay, but here we have carrier sensing and we have collision detection. So the collision detection is done in the sense that while you are sending the frame, you have to keep listening to yourself in addition to listening to all other signals from all other nodes in the network. So that's what we mean by a collision detection. And we said that this is done through basically listening to the energy level, as we will explain in the next slide. So this means that I start the transmission, and while I'm transmitting, I'm actually receiving or listening, okay, for any collision that might happen. So this is illustrated by this loop here, that while you are transmitting, you have to also listen to yourself, whether the energy level is one energy level that indicates that the only one who's transmitting on the shared medium is you, or if it's slightly above or significantly above, this means that you're not the only one who's sending on the cable right now, which means that there is a collision. Okay, so this is illustrated by this loop here, that while you are sending, while you are transmitting the bits one by one, you are also receiving to make sure that a collision is happening or not. So if for any reason while you are transmitting that the collision happened, okay, this means that I need to perform I need to do two things. Okay, If the collision did not happen, which means that I finished this loop and I finished transmission and there's no collision, this means that, okay, I'm done. Okay, so that's that part, you're done. Once you're done, then you have to go to the start to see if you have to send any other frame. So if there is a collision, if you detect a collision, then this is the third major difference. Again, in pure Aloha or slotted Aloha, detection is detected implicitly by not receiving the acknowledgement, right? So in pure Aloha or slotted Aloha, I don't actually perform carrier detection. I don't actually measure any energy level. Okay, so if I want to send, I just send, whether it's slotted or asynchronously in pure Aloha. And then if I don't receive the acknowledgement, then that means that either the signal that I sent is not decodable or there was a collision. So in that case, I detect implicitly, not explicitly, that there was a collision or there was some error. Because here, the good news is that through this measurement of the energy level, I can in fact detect the collision explicitly. So in that case, the third major difference is that you need to send a jamming signal. Okay? So the jamming signal is a clear sign for not only for you, but for all the nodes on the shared cable that currently there is a collision. Which means that this frame will not be decodable, and you have to perform the retransmission procedure. So starting from here, all the way, this is exactly the back-off procedure which we did for pure Aloha or slotted Aloha. Okay, so this is one major difference, that's another major difference, and this is the third one, the jamming signal. Okay, so the jamming signal is a small signal that I send once I detect the collision to indicate to everyone on the shared medium that there is a collision. Just a side note, which is not even mentioned in the book. I mean, someone might wonder, I mean, if the jamming signal is sent while there is a collision, how can the nodes detect the jamming signal and recognize it while a collision is happening on the channel? Yani, currently there is a collision happening on the channel. Once I detect the collision, I just send the jamming signal. Okay? So how can others detect the jamming signal while there is a collision on the channel? I mean, if they decode the jamming signal, if they are able to decode the jamming signal, they might as well decode the signal, the original signal that I'm trying to send, right? But they can't. They cannot decode the signal that I'm trying to send. So how can I send the jamming signal on top of that, and they will be able to recognize it? What happens is that this jamming signal is sent on a different frequency. Okay, that's the only way for the nodes or for the stations to recognize the jamming signal. So you have, so it's like you have the channel. This is like the data channel, and you have a small out of band signaling channel here. So the jamming signal is sent over this channel. So it will not interrupt the data transmission. So the jamming signal, they call it out of band signal. Okay, so this way the stations will recognize this jamming signal and extract it, even if there is collision on the shared medium. Okay, any questions? So those are the three major differences. As we said, for energy level, we have three different energy levels. So we have two thresholds basically. Okay, if it's below the first threshold, this means that I don't have any transmission happening. So it's here. If it's below the first threshold, this means that it's just noise, but no one is actually sending anything on the channel. This means that the channel is idle. If it's above the first threshold, but it's below the second threshold, this means that if it's above the first threshold, this means that there's someone is sending. And if it's below the second threshold, this means that this one who is sending is the only one who is sending. Okay? So it's like I have one threshold here, and I have another threshold here. Or actually, it's slightly below that. Okay, so if it's above the first threshold, this means that there is someone is sending, and since this is below the second threshold, this means that someone is sending and there is no collision. Okay, if it's above the second threshold, this means that there is more than one sending at the same time, which means collision. So that's simply how the energy level indicates the three different states. So using two thresholds, I was able to detect three states: idle, frame transmission, or collision. So I need to have two thresholds in that case. Okay? So any questions?
Again, where's the second threshold?
The second threshold usually is almost double almost double the power level. So this is like, if we assume that this is, for example, P1. So usually this is close to 2P1, which means that more than one station is sending at the same time, which means collision. Okay. Of course, this level depends on the transmission power. This level depends on the transmission power that you use, which is part of the standard. So, for example, Ethernet dictates, let's say, maybe like 1 milliwatt for frame transmission. So this means that this threshold should be slightly less than 1 milliwatt to indicate that if it's 1 milliwatt or slightly above, this means that there's one frame transmission. And if there is a collision, this means that you are getting close to slightly less than 2 milliwatts. Okay? Or around 2 milliwatts. So this means that there is a collision. Or maybe it could be more than 2. If there are three frames, three stations are trying to send at the same time, or 4 stations. But for me, I don't care. If it's more than 1, it's a collision. Whether it's 2 stations, 3 stations, 4 stations, whatever, it's still a collision. Okay? So the good thing about Ethernet is that this energy level detection is easy. Why? Because if I have one node and it's trying to send, okay, with a specific power level, the node here, if it goes on the cable, the amount of attenuation for the signal on the cable is really, really low. So if I'm sending 1 milliwatt, chances are here it will be almost 1 milliwatt. with no attenuation whatsoever, because it's a wire. A wire sort of focuses the energy of the signal in one direction. So the amount of attenuation that the signal encounters is really low. Okay? That's why we say that even if there are two nodes on the extreme points of the cable, if I send one signal on one point, the other station on the other side of the cable should hear almost the same energy level. It takes time through propagation and whatnot. But we're not talking about time here. We're talking about energy level. So that notion facilitates the concept of collision detection. It's easy. So on a cable, on a wire, it's easy to perform collision detection. For another case, if the shared medium is wireless, okay, we cannot do that, because if the station is sending, the energy of the signal dissipates in all directions, right? Unless we're talking about directional antenna, but in general case, the energy is dissipated in all directions. So in that case, if I have two stations in wireless, depending on the distance between them, the energy level that the other station will see is different, is significantly different. So if you are like 2 meters far, you will detect an energy level which is maybe slightly less than the original transmission power level. If you are like 4 meters away, it will be significantly less. If you are 10 meters away, then it will be very low. So in that case, it's very tricky for me to use this threshold concept to detect the collision. In other words, in wireless, it's very tricky to detect the collision because of the variable energy level due to several factors, due to attenuation. And we talked about different types of noises, right? We talked about impulse noise, we talked about thermal noise, we talked about all types of multipath fading noise, right? All these type of noises did not happen in the case of the wire, because for the case of the wire, the energy is focused, is going in one direction, it's contained, so there's no attenuation. The amount of noise that comes from outside is really low, is minimum. So that does not really affect the signal that much. So the conclusion is, for wireless, we cannot use collision detection. Okay? So we have to look for some other ways to perform more or less the same functionality. And it turns out that for wireless, they try to use the concept of collision avoidance, not collision detection, because detection is not possible. So the concept of collision avoidance is the fact that we perform similar to more or less the P persistent. We'll find lots of similarities between this and the P persistent with some tweaks. Okay? So the first thing that we should do is to perform the continuous sensing. Again, similar to the P persistent, we sense continuously until we find that the channel is idle. So again, if we start sending right away, this increases the possibility of collision. And for the case of wireless, the collision is more expensive. Why? Because I cannot detect it. At least for the case of wired transmission, when the collision happens, I can detect it, so I can recover from it very fast. Here, I cannot detect it right away. If there is a collision, then I have to wait for significant amount of time before I can implicitly recognize that there was a collision. And we'll see that there is an indirect way, similar to the pure Aloha. If I don't have any way of detecting the collision, then I have to time out and wait for acknowledgement. That's the only other way, right? But which makes the cost for the collision more expensive in that case. Why? Because I have to wait for a significant amount of time before I recognize that there was a collision and recover from it. If there is collision detection, then I send the jamming signal right away and everything will abort, and they will start taking the back-off procedure. Here, I don't have this luxury, so I have to look for another way to resolve or to try to avoid the collision rather than detecting the collision. So in that case, the carrier sends CA, or the carrier sends multiple access with collision avoidance. What happens is that it waits for what we call a interframe spacing. Okay? So the first thing I should do is that even though the channel is idle, but I have to wait for interframe spacing. What happens is that the interframe spacing accounts for if there is any channel which is far from me, which recognize that the channel is idle and is trying to send, let's wait until I make sure that the channel is really, really idle. Okay? So that's the first thing I have to do to avoid collision. Again, I cannot detect collision. So interframe spacing indicates that I cannot sense that I cannot sense any transmission happening on the channel now. But maybe there is someone who's far, okay, and he is sending, and I cannot really hear him until now. So let's wait a little bit. So that's what this interframe spacing means. So the interframe spacing as well can be used to represent some kind of a priority. So the first thing is that this accounts for if there is any transmission happening, but I cannot hear it. So I have to wait a little bit until I make sure that no one is actually sending anything. The second thing is that through this interframe spacing, I can perform some kind of a priority scheme. So if all of us detect that the channel is idle, okay, and I give you interframe spacing which is slightly less than another station, what does that mean? This means that you have a higher priority or lower priority? Higher priority, bravo. Why? Because this means that the next time you will try to access the channel, it will be before the other station. So that means that you implicitly have higher priority because you have to wait for a shorter amount of time. Okay? Okay, so we will all have to wait for interframe spacing. So once the channel is idle, I will wait, you will wait, everybody will wait for interframe spacing. Whether this interframe spacing is different for each station or it's fixed, we all come down to this point here. Here. Okay? So we all waited for interframe spacing, and now let's just access the channel. We made sure that, of course, after the interframe spacing, we do sensing again. And again, the channel is idle. Okay, so let's hit the channel. Of course, again, there is a possibility that two stations have waited for interframe spacing, and they waited for more or less equal interframe spacing because they discovered the channel is idle at the same time. So they come here, they try to send, and they collide. Well, for the case of P persistent, I resolved that using the probability, right? Here, we will use a similar procedure for the back off. Okay? We used a similar procedure which is called binary exponential contention. It's not a back off because the collision did not happen yet. right? But it's exactly similar. So again, the first time we'll use k equal 1, okay, which means that we have a window of 0 or 1. Every one of us will generate a random number, which means that if this random number is 0, I will send at this point. If this random number is 1, I will wait for one time slot and send in this point here. Okay? If the collision happens, then the next time k will equal to 2, which means that the window is 0, 1, 2, and 3, which is 2 to the power 2 minus 1. So 0, 1, 2, 3, and then we will perform the exact same thing. We will generate a random number between this window, and either you wait for no time slot, or one time slot, or two time slots, or three time slots. Which means that in order to avoid collision, we perform a similar backoff procedure even in the first transmission. Okay? So we will not wait until the collision happens and then we perform the backoff procedure. In order to avoid the collision, we will have to perform the backoff procedure even in the first transmission. But that happens after the interframe spacing. So the first thing is, the first major difference again is we have to wait for interframe spacing. We didn't have to do that for CSMA CD, right? Second thing is we have to perform a procedure which is similar to the backoff procedure in the first transmission. Again, we didn't have to do that for the carrier sensing with collision detection. The third thing is that, of course, since we cannot detect the collision, right? So the only way for us to know that the collision has happened is that we have to time out. We have to wait for acknowledgement, and then if we time out before we receive the acknowledgement, this means that most probably a collision has happened and we have to retransmit. Again, we didn't have to do that for CSMA CDY because we were able to detect the collision. Once we detect the collision, we send the jamming signal which aborts everything. Okay? So we don't have to use acknowledgement. We don't have to wait for the acknowledgement. We detect the collision without even using any acknowledgement. But here, we cannot do that. So the only other way for us to recognize that there was a collision is by waiting for a specific timeout. If we receive an acknowledgement from the receiver, this means that everything is fine and there was no collision. There is no energy measurement here. I cannot use energy measurement. So these are the three major differences that I need to use to avoid collision rather than detecting collision. First thing is interframe spacing, and then binary exponential contention procedure, and then the third one is acknowledgement. Okay? So it might sound a little bit, overhead for you that, you have to really do lots of things to avoid collision, but that's true. In wireless, it's very, very tricky. You do have to really perform lots of things to try to avoid collision. Why? Because collision, if it happens, it's very expensive. It's very expensive. So you have to spend a little bit of time to make sure that you actually really avoid the collision from happening. And even with this sophisticated procedure, there are still some scenarios that are not covered by this. And only performing this procedure in wireless is not enough. So we see maybe some of you have come across the hidden terminal problem or exposed terminal problem. So these type of scenarios are not covered by this. So if you have hidden terminal problem, chances are you will encounter so many collisions even by performing this. Okay? So this procedure assumes that you are in the range of everyone in the network. You are in the range to listen to everyone in the network. So in that case, this procedure will work more or less fine. You will get reasonable amount of efficiency, not 90% like the case of CSMA CD. Here it's slightly less. But you will get reasonable efficiency even for the case of wireless. But this is assuming that you are in the range to listen to all other stations in the network. But that's not guaranteed. In the case of wireless, it's not guaranteed. So if you are in a mall and you are trying to perform some wireless communication, maybe someone else is on the other side and you cannot even listen to what he's sending. It's sending. So you send at the same time to one intermediate node. You can see this node, he can see this node, but you cannot see him and he cannot see you. You see that scenario? This is the hidden terminal problem. So it's basically in wireless you have one node here, and you have intermediate nodes, and you have another node here. So you are in the range of this. He is in the range of the same node. But you cannot listen to what he is sending. You are totally out of range. So in that case, you listen, you wait for interference, you do whatever you want. You cannot really listen to what this station is sending, right? So chances are each of you will perform interference spacing, contention procedure, whatever. You will send, and the collision will happen where? At the intermediate node. So in that case, what will happen? You will not receive acknowledgement, which means that the collision has happened, and you will keep doing that over and over again. So this is called the hidden terminal procedure, and to avoid this, you have to use extra procedures on top of this procedure to avoid the hidden terminal problem. So believe it or not, even with this sophisticated procedure, it's still not enough to avoid the collision in certain scenarios. And the main reason for that is that the transmission range for wireless is not, you cannot say the transmission range is like 100 meters. Yes, okay, so you can set the power to set the transmission range is 100 meters, but you cannot prevent someone else from 200 meters away to send to the same destination you're trying to send to, right? You cannot stop that.
But it won't receive anything, right? If the range is 100 meters.
If the range is 100 meters, then you can receive from this node. You can send and receive to the intermediate node, right? And he can send and receive from this intermediate node. So this node is in the range of both of them, but unfortunately you cannot see each other. This is the problem. This is what we call hidden terminal problem. That's why it's called hidden terminal problem. So even with that procedure, it's not enough to avoid scenarios like hidden terminal problem. The exposed terminal problem is even more complicated, so I won't go through it. Okay. So as a rule, of course, as we said, that interference spacing, in addition to the fact that it's used to make sure that the channel is really, really idle by waiting for a certain period of time, to make sure that if there is someone far and he's still trying to send, that the signal is not yet at your location, so you have to wait for slightly more time, which is the interference spacing. And we said that the other purpose for interference spacing is that it can also be used to define certain priority scheme. So I can give to one node interference spacing which is shorter from the same interference spacing for another node, in which case this node has higher priority. And in fact, for 802.11e, because we have different versions, 802.11e uses that exact same concept to provide different priorities for different stations. Okay, so we actually teach that as part of the course multimedia networks. In multimedia networks, you will learn the concept of quality of service and how it can distinguish between the different stations in different standards. Okay, طيب. In CSMA CA, if the station finds the channel busy, yeah, so that's another very important concept. We said that during the contention window, okay, depending on the random number you generate, we can wait for 0 time slots, which means that you send right away, or maybe you can wait for 1 time slot, or 2 time slots, or 3 time slots, or 4 time slots, depending on the random number you generate, right? But regardless of this random number, every single slot you have to resense the channel again. That's a very important point. Okay? Because if I have to wait for 3 time slots, and then after 1 time slot, someone else tried to send, what is the point of me waiting for 3 time slots if someone else has started a new fresh transmission? This means that after 3 time slots, after 3 time slots, then you will sense the channel and find it busy. So I can find it busy right away. So what happens is that during the contention window, every time slot you have to sense. At the end of every time slot, you have to sense the channel again. Okay? Type. So what happens if maybe I have a random number of 5 time slots. Okay? After 2 time slots, I found that the channel is busy. What do I do? Wait. Wait for another time slot. But the new fresh transmission may take longer than a time slot. Okay?
You have to wait for it to end, then wait the inter-frame spacing again.
This is good, but you know what that means? Is that it's like you kick someone from the middle of the line and tell him, go to the back of the line. Is that really fair? No. So what happens is that once I detect that the channel is busy, I will suspend the timer. I will not reset. I will suspend the timer. Which means that, okay, someone else is in service now, I will keep my turn in the line. But I will pause until his service time is finished. I don't know how long he will take. Okay? So after he finishes, I will restart my timer again. So if you have a random number of 5 time slots, after 2 time slots, you find that the channel is busy. You suspend the timer. The timer will have to wait for another 3 time slots after it finds that the channel is idle. It doesn't have to wait for interframe spacing again and redo the whole thing from scratch, right? Because then this means that I lost my turn. So to preserve my priority in line, then I only suspend the timer and restart it once the channel comes back idle again.
Hake time slots won't be equal, huh? If you suspend and you wait, like, for example...
No, the contention time slots are equal. The data frame, the frame transmission time is variable. So once you start a frame, I can listen to what you send, right? And you know what? Not only that, I can decode it. And I can sort of recognize the frame length that you are trying to send. And I may be able to estimate the transmission time for your frame. Which means that I may have some information about when the channel will become idle. But even if I don't know, I will do what? I will do continuous sensing. Okay? My timer is suspended. I will do continuous sensing. Once I find that the channel is idle, now I restart the timer, which will wait for 3 time slots, the 3 remaining time slots, and then I start to send. But again, if I wait for 3 time slots, what will happen? After each time slot, I will keep sensing the channel. Okay? So during the contention window, for every time slot, you have to sense the channel. So this concept talks about the fact that if you set a random number, and then in the middle you discover that the channel is busy, in order to keep your turn, you only suspend the timer and restart it once the channel comes back idle again. So this creates some kind of fairness amongst all the nodes. It creates some kind of fairness. Why? Because if I had to wait for 2 time slots waiting for the channel to become idle, right? And you kick me at the end of the line, so I have to go back from scratch again. So it doesn't make sense. And, you know, this time I generated a random number of 5. Maybe when I generate a random number again, it will become 10. Okay? So using this concept, we can, of course, I mean, you cannot feel it because you don't have the sense of statistical concepts. But this is done through some MATLAB simulation and things like that to really make sure that this concept will perform fairness.
If at the second time slot, okay, it finds the channel busy. Okay, so it should wait, pauses, and wait.
Right.
Until the channel becomes idle again.
Right.
Okay, so there will be a gap.
Right.
Time between the second time slot and the third one. So this will be counted as like I feel like the second time slot will be longer than the other slots. That's
No. While you pause, this is data transmission time. It takes whatever. Okay? Once the data transmission is done and you are idle, then if you are not doing any kind of waiting, then you have to wait for interframe spacing and perform the procedure from scratch. But you have been waiting, you have been in the contention window. Which means that contention window means what? Means that you are interested in sending and you have taken your turn in the line. Okay? So once you take your turn in the line, it's not fair to tell you, go to the end of the line again and perform interframe spacing and then go to the contention window from scratch. In order to provide this fairness, then your contention window will start earlier than others. That's what this means. You don't have to wait for interframe spacing anymore. You will have to wait for 3 remaining time slots. But guess what? I mean, after each time slot, you have to sense. So in a way, implicitly, you have to wait for some time, which also maps to interframe spacing. But this is for you not interframe spacing. It's actually the contention window. You have passed the stage of interframe spacing and you have taken your turn into the contention window. So instead of kicking you out of the line, then we give you some priority the next time because you have been waiting. That's what this means. The time in between is variable time. It's transmission time. It takes whatever, even 2 seconds, 3 seconds. This is not part of the contention window. It's like you have divided the contention window into 2 parts, and in between there is a variable time of transmission. Because you know what? I mean, this procedure is done in a distributed way at every station. So every station performs this procedure independently. Okay? Every station will perform this procedure independently from others. And again, this procedure, the good thing about it is it's distributed. I don't have to synchronize anything. I don't have to do any special handling. But at the same time, it does not guarantee no collision. Collision may still happen. So if a station decides to divide the contention window into 2, that doesn't mean that all other stations will do the same. only this station will perform it this way. We'll divide the contention window into 2 time slots, and then it finds that the channel is busy, so it waits for a variable time until the channel becomes back idle again, and then it waits for the remaining 3 time slots. And regardless, during the contention window, every time slot you have to resense. Okay? So, based on that, we can see that there are some major differences compared to the CSMA CD. The first thing we notice here is that the back-off procedure is not done only when there is collision. It's actually done here. Okay, which is the contention procedure. So I will not wait until the collision happens to perform that contention procedure. I will do it even in the first transmission. Okay? So I don't need to repeat it again here, because it's done with every single transmission. So that's one major difference. Before that, there is, of course, if the channel is idle, then I have to wait for interference spacing. And then I have to do the contention procedure, which means that choose a random number based on the value of k. So initially, k is equal to 1, so I generate a random number between 0 and 1, and so on. Type. And then wait for r time slots, and during the wait, here, it says after each time slot, I have to check that the channel is still idle. And if the channel is busy, all I need to do is just to suspend the timer. Okay? Wait for all the R time slots, whatever. R is the random number that I generated. Channel is still idle, so send. After you waited all the time that you need, send. Again, that does not eliminate collision. Collision may happen. In which case, the only way for me to recognize that the collision has happened is by not receiving acknowledgement. Right? So in that case, I have to wait for a timeout. Did I receive acknowledgement? So this part is similar to pure Aloha. Because again, in pure Aloha and slotted Aloha, we didn't have any means to detect a collision. So we had to rely on acknowledgement. Same here. We don't have a way of detecting collision, so we do some kind of avoidance, which is what we have done here, but for recognizing whether there was a collision or not, we have to use the acknowledgement. Okay? And if we don't receive acknowledgement, this means that there was a collision, or maybe the signal was not decoded on the other side. For me, it's the same. The reaction for me is that I have to do retransmission. And in that case, I have to increment k and check if the k is k maximum. And again, if I reach 15 times and I did not, and there was a collision at every single time, then I abort. When I abort, this means that, okay, this frame I cannot send, just throw it away, take another frame, and perform the same procedure. Reset K and perform the same procedure again. And again, that doesn't mean that the frame that I throw away, this was the end of the world for that frame, but maybe if I'm using TCP from the transport level, this frame will come down again in the stack and it will take its turn again for transmission. But if I'm using UDP, then, okay, it's done. Okay, so any question? So again here, 3 major differences. 1, interference spacing. 2, contention procedure. 3, the concept of acknowledgement. 4, implicitly detecting the collision. Okay? So this is the end of one major category in the medium access control techniques, which what we call the collision-based techniques, okay, or random access techniques. For random access techniques or collision-based techniques, we actually try to access the channel together, and if there is any collision, then we will resolve it using different schemes that we talked about. So we talked about pure Aloha, which is totally asynchronous, complete freedom, or slotted Aloha, which creates some kind of restriction using the time slots, and using the time slots, we were able to increase the efficiency of the channel a little bit. Of course, not much, because we don't actually, when we try to send, we don't have any way of sensing whether someone else is sending or not, so the probability of collision is high. So to reduce that, we have used the concept of a carrier sensing multiple access. So for using carrier sensing multiple access, it's like when we go to the roundabout, we have to check around to make sure that no one else is in the roundabout before entering. The good thing, if our shared medium is actually wired, then in that case, we can detect if there is a collision or not. We can detect it right away using the energy level. So in that case, I can recover from it very fast. I don't have to wait for acknowledgement, and I can just send the jamming signal once I detect, and this way I can resolve the collision. If I don't have any way of detecting the collision explicitly, then I have to resort to the concept of collision avoidance, in which case we have to avoid the collision using different ways. One is the interference spacing, and then the contention procedure, and then if there is any collision, then I will not receive the acknowledgement. Okay? This category talks about a totally different concept. Here, we will try to organize the access of the channel using a moderator or using some kind of a coordinator node. It's like we are in a meeting, and someone really dictates who can send on the channel. So if I can do that, then I lost the notion of distributed access. The good thing about the random procedures or contention-based procedures is that I don't have to do any coordination between the nodes. All the nodes are distributed. Each one of them performs the procedure independently, whether it's Aloha, pure Aloha, whatever. It doesn't have to check with any other node. So it accesses the channel randomly. Here, it's centralized in a way. So someone has to really be the controller of the whole network. By doing that, I can eliminate the collision completely. That's why this category is called the collision-free protocols. Okay? So the only way for me to eliminate collision altogether is by having a moderator or coordinator or a controller who actually can control the access to the channel. He's the only one who can say, you can send now, which means that no one else is sending, because he does not have control. So in that category, we will study two. In the book, there are three schemes. The third scheme, which is the token passing, but this token passing is actually very much obsolete. Nobody uses it. So that's why we will not go through it. So here we'll talk about the reservation-based scheme and the polling scheme. So the first reservation access method is that the controller allows for many slots at the beginning which are equal to the number of stations in the network. So here we have 5 different stations in the network. Okay? So in that case, the controller will allow for 5 different many slots. Each of these slots correspond to one station in the network. If a station has a data to send, okay, then the station will send one in the many slot assigned to it. Okay? So this is similar to time division multiple access, which we will study later. But here, this is not data. Remember, this is just a flag to indicate that I have a data to send. Take that in mind. That's it. So this is a control signal. It's not the data. This is a control signal that a station tries to send to indicate that indeed I have data to send. So please allow me to send. Once this many frames finish, then the controller will give the control to one station at a time to send, in the order of the many slots. So the order of the many slots is 1, 2, 3, 4, 5. Then station 1 will send first, and then it happens that station 2 does not have any data to send. That's why this many slot is 0, right? So in that case, I don't have any gap for station 2, right? So because here only station 1, station 3, and station 4, so I only need to send or allow for the transmission of 3 frames. Okay? After I allow the transmission of sending 3 frames, then I send the many slots again. In the many slots, only one station has data to send in that case. Then it's one data transmission. And then after that, I go to the many slots again. So again, this concept so you need to have a controller who controls these many slots and which station to send in which order. So you need to have, it's like we are in a meeting, and then before we start, I say, okay, who has a word now to say? So 3 people raises their hand. So I say, okay, you go first, then you go second, you go third. And after we finish the first phase of discussion, we say, okay, who has a question now? 3 people raise their hand. Okay, so you go first, you go second, you go third, and so on. Okay, so that's what the reservation means. So this way, we will never have collision. Right? We will never have collision. As long as the controller is alive. Okay? If the controller is alive, the whole network is dead. If the controller is dead, the whole network is dead. Right? So this is the reservation access method. It's based on this reservation many slots. Okay? In the reservation many slots, I don't want to confuse you, but in the reservation many slots, here I used a concept which again prevents collision in that phase. Okay? So in that case, I used many slots which are equal to the number of stations in the network. And if a node wants to send data, then it sends one in the many time slots, and the many time slot which is assigned to it. Okay? Another variation of this, which is not in the book, is that this reservation many slots uses CSMA CA, uses some kind of a contention technique. Okay? So that's another variation of the reservation base, which means that I allow any station to send at any slot. It's not like predefined slots. Okay? And if there is any collision, this means that if a collision happens between these 2 stations, this means that the controller will ignore both of them. So both of them are not allowed to send. But in that case, the many time slots can be much shorter. Because if I have like 1,000 nodes in the network, and I have 1,000 many slots, so imagine how much time I have to wait every time to recognize that only one station in the whole network wants to send. Okay? So instead of doing that, we allow the many slots to shrink, okay? And instead of assigning one separate many slot for each station, we allow them to contend on the channel. And if there is any collision, tough luck. Okay, so both of them are ignored. Okay, but at least if there is one station wants to send amongst 1,000 stations, then I have to wait for 2 or 3 many slot duration. I don't have to wait for 1,000 many slots. What I'm trying to say is that this is the reservation phase. The reservation phase may use any of the techniques we have studied before or will study after, whether random access techniques or channelization techniques. Okay? But this is done not in the data. This is done for reservation. So first we have to have a reservation phase prior to the data transmission phase. At the end of the reservation phase, we have clear information who is eligible to send. So I say, you send, you send, you send, that's it. And then we repeat that again next time. So that's the first concept. The second concept is what we say polling. Again, we have a main controller. Here we call it the primary node. The primary node has to be part of the transmission. The primary node must be either the sender or the receiver of the data. What does that mean? This means that if we are in a network, let's say this is station 1, this is station 2, this is station 3, okay? And we have the primary node here. So station 1 wants to send data to, let's say, station 2. Okay? It cannot send this data right away to station 2. It has to first send it to the primary node, and then in one phase. And then after the primary node receives this data, the primary node will then send it to station 2. Which means that for the polling mechanism, the primary node has to be part of the data transmission, either the sender or the receiver. Even if 2 stations want to send to each other, they have to send it through the primary node. And this is in fact what happens in some standards, like مثلا 802.11. For Wi-Fi, 2 stations cannot send to each other directly, right? Even for cellular, 2 stations cannot send to each other directly. We always have the concept of uplink and downlink. Uplink meaning that stations, they send to the primary node. The primary node is the access point or the base station. Downlink is when the primary node sends to the stations. Okay? But we cannot allow for direct transmission from the stations in one shot. We cannot do that. We have to do it on 2 different steps. One is to send to the base station or to the access point, and then in the second step, we send from the access point to the stations. So that's a condition, that's a very important condition for the polling mechanism to happen. So in that case, the primary node can either send data to the station or get data from a station, from one station. Okay? So the way that the polling function works is that this concept talks about, or this scenario talks about the downlink transmission. And this talks about the uplink transmission. In the downlink transmission, the primary node is always the one that initiates the transmission, even if it's the receiver. Even if the primary node is the receiver, it's always the one that initiates the call or initiates the transmission. So for example here, the primary node wants to send data to one of the stations. This is what we call the downlink procedure. Downlink is coming from the access point to the stations. So in that case, first it sends a control signal, which is called the select signal. This is a very small short signal. And it sends it to one station to tell that station, I selected you, I want to send you something. Okay? Only if that station says positive ACK, which indicates, okay, I'm ready to receive what you are trying to send me, then I send the data and wait for acknowledgement. Okay? So first I have to select. That's why it's called polling. Polling معناه polling, I'm polling you, I'm selecting you. Either I have a data for you or I want you to send data for me. I always have to select, I always have to point to one particular node only. One node at a time. Unlike reservation. Reservation, I allow multiple stations to send, okay, based on this many time slots. But here, I select one at a time. Okay? So first I have to select one particular station, and then if that station is ready, if that station is not ready, then it will send me a negative acknowledgement, which means خلاص, I selected it and it's not able to receive data, so I go to another one, and I will come back to it later when it's ready. Okay? But if I receive acknowledgement, this means that this station is ready to receive data, so I send the data and wait for acknowledgement. Okay? So in that case, when I send data, although there is no collision, but I have to wait for acknowledgement. This means that maybe I send the data and it's not decodable in that case. I wait for acknowledgement not because there is a possibility of collision, because there is no possibility of collision, but because there might be some noise and this signal has reached to B, but B cannot decode it due to some noise. So in that case, it will send me negative acknowledgement, not acknowledgement in that case, which means I have to retransmit it. So this is the polling mechanism in the downlink direction. In the uplink, we send a select control signal as well, which is called poll. So there's no difference between the two signals. The only difference is that this is for the uplink and this is for the downlink. That's why it has different name. But the actual function of this signal is actually the same. I'm selecting you. Either I have data for you or I want you to send data for me. Okay? If I want you to send data for me, then maybe you don't have data for me. Okay? So in that case, you will say negative acknowledgement. I don't have anything for you. So, okay. So this means that I asked you, you don't have data for me. So next time, after some time, I will send another pulse signal. And this time, if you have data for me, you will send me the data directly. Okay? Once you send me the data, I will send you the acknowledgement. So, so one thing to pay attention to is that the handshaking for the case of downlink is based on 4 different stages, whereas for the uplink is based on the fact that it's based on 3 steps only. Why? Because if I'm polling you, this means I'm ready to receive from you. I don't have to wait. I don't have for you to ask me again whether you are ready or not. I'm polling you, which means I'm ready to receive from you. So you don't have to ask me whether you are ready or not. Okay? So that's why the 2 and 3 steps are merged together in one step. Okay? So pull, if you have data for me, then you will send the data directly. You don't have to ask me for anything. Send the data and then acknowledgement. So pulling is based on the fact that I'm always asking people whether to send me something or I have data to send to you. Okay? So the pulling mechanism is, there is some kind of an overhead. As you can see, in order to avoid collision, I have to send so many control signals, right? I have to pull every single time. And maybe all these control signals will be an overhead, will be wasted. Why? I'm selecting you, I don't have data for you. I'm selecting you, I don't have data for you. So, but I have to always keep asking you. But by doing that, I was able to eliminate collision. So there is some kind of an overhead on the primary node. Every time it has to ask. But that's the only way I can avoid the collision. The other thing we need to pay attention to here is that the order of the selection has some implicit meaning. I select the nodes in a particular order, which implicitly indicates the priority of these nodes. The primary node may actually ask one node more than the other, which means that this node will implicitly get more priority than the others. So by controlling the order of the pulling, I can in fact create some kind of a discrimination between the stations. Okay? Okay, we'll stop here.